Femtosecond lasers offer a new route away from PFAS. Manufacturers looking to reduce their reliance on per and polyfluoroalkyl substances, PFAS, may have another option to consider: changing the surface of a material instead of coating it with chemicals. Femtosecond lasers use pulses lasting roughly a quadrillionth of a second to alter materials at microscopic and nanoscale levels. By creating carefully controlled surface structures, the technology can change how water interacts with a material and, in some applications, produce water-repellent properties without a fluorinated coating. Lithuanian laser manufacturer Littlelit is positioning ultra-short pulse laser processing as one possible tool for companies evaluating PFAS alternatives. The approach is not a direct replacement for every PFAS application, but it could give manufacturers another route where surface texture can deliver the required performance. PFAS restrictions put surface treatments under scrutiny. The push for alternatives is becoming more urgent as PFAS regulations expand. The chemicals have been widely used because they can provide resistance to water, oil, heat, stains, and corrosion. Those properties have made PFAS useful in products including textiles, electronics, furniture, construction materials, and industrial components. In the United States, states have increasingly moved beyond regulating individual PFAS applications. According to figures cited by the Safer States Alliance, at least 31 states were expected to consider PFAS-related policies in 2026, covering areas such as product restrictions, drinking water, environmental cleanup, and sludge disposal. States including Maine, Minnesota, and New Mexico have pursued broader approaches targeting products containing intentionally added PFAS. For manufacturers, compliance is only part of the challenge. Removing a PFAS-based treatment can affect product durability, moisture resistance, corrosion protection, and production economics. A replacement, therefore, has to work technically while also fitting into a practical manufacturing process. That is where laser-based surface engineering could become relevant. Femtosecond laser pulses can remove or restructure very small amounts of material while limiting the amount of heat transferred to the surrounding area. Manufacturers can use that precision to create micro and nanoscale patterns that change surface behavior without applying an additional chemical layer. Littlelit CEO Nikolajus Gavrilinas has said the process can be used to create water-repellent properties on certain materials. Potential applications could include metals, glass, stone, and some building or interior products where moisture, ice, or corrosion are concerns. The same type of processing can also be used to alter a surface's appearance or other functional characteristics. Metal fittings, handles, and decorative components, for example, can potentially receive colors, patterns, or textures through laser treatment rather than conventional paints, inks, or related surface finishes. The key distinction is that the function comes from the engineered surface itself rather than a material applied on top of it. Scaling femtosecond lasers for industrial manufacturing. The technology still faces a familiar manufacturing question. Can it perform economically at production scale? A laser process that works in a laboratory or specialized application must still meet requirements for cycle time, equipment cost, reliability, maintenance, and integration with existing production lines. Those factors will determine whether femtosecond processing can compete with established coating and finishing methods. Littlelit has been expanding its manufacturing capacity as it targets wider industrial adoption. The company began construction of a factory in Vilnius that it says is designed to eventually produce as many as 3,000 femtosecond lasers per year. Its systems use technologies developed by company co-founders Kęstutis Rogelskis, Nerijus Rusteka, and Gavrilinas in collaboration with Lithuania's Center for Physical Sciences and Technology. Higher laser production alone, however, will not make the process a viable PFAS alternative. Manufacturers will also need to evaluate how quickly surfaces can be processed, how long the resulting properties last, whether the technique works with their materials, and how easily the equipment can be added to existing operations. Cost per component will be another major consideration, particularly for high-volume products. That makes femtosecond lasers less of a universal PFAS replacement and more of an additional manufacturing technology worth evaluating. For applications where water repellency, Corrosion resistance or other functions can be achieved by modifying the physical structure of a surface. Ultrafast lasers could reduce the need for certain chemical coatings. As PFAS restrictions continue to reshape material and process decisions, that capability could give manufacturers another option when redesigning products and production lines.